I got to read the biography. Okay, so it's my pleasure to represent the math department to introduce you to Xiaoming Wang as our colloquium speaker. So Xiaoming got his PhD from Indiana University. He was advised by Roger Temam in 1996, and then he spent the next 2 years at New York University as a Quran instructor. He then moved to Iowa State, where he was a colleague of Brown Smith for a couple of years, I suppose, and was promoted to associate professor with tenure in 2001. And then he moved to Florida State in 2003. Now he's a full professor and the chair of the math department at Florida State. So his main research interest is in applied PDE, especially those that arise in fluids and geophysical fluid application. He's also interested in turbulence theory, dynamical system, and numerical analysis. So today he's going to talk about flows in karstic geometry. So the floor is yours.
Thanks, John. Thanks for the invitation. It's really nice to come here and meet old friends and get to know new friends. John told me I should make the talk somewhat accessible to the general audience, so I have to apologize to the experts. Some of it would be very pedestrian until we get to the very end of it. So what I'm going to talk about today is flows in a special structure called Karst. I'll give an outline, introduction of the problem, talk about the main issues, then focus on the single phase flows in Karst geometry, then talk about talk about two phase flows in Karst appliances.
Just going to make it full screen.
Okay, so what is Karst? Here is a typical Karst of a landscape. You have limestone or dolomite. Because of geological processes, caves, conduits would form within these rocks. So essentially, Karst is this kind of a landscape. So you can think about rocks with caves inside. Okay. And a very well-known example is this so-called Minerve Karst in the southern part of France. So you can see these rocks and the caves over there. But Karst itself, the name comes from a region from former Yugoslavia. I forgot whether it's Serbia or Croatia. But it's a beautiful place. Similar to in China, it's a Jiuzhaigou. Looks very beautiful. It's Karst region, and so these I have something close to home that is related to Karst. So a local tourist attraction is called the Wakala Spring, which is about 15 miles away from Tallahassee. This is according to the U.S. Geological Survey, the second largest freshwater spring in the world. So water gushes out here. Long time ago, before Hollywood was really built, people used this site to film films. For instance, the first Tarzan film was filmed right over there. So if you go, I don't know, Ralph, your host ever treated you there? Okay, so you have seen it. Mark, you have to go again sometime. Look at it. There's a place over there, so people filmed at the first Tarzan, and also Airplane 77, but somewhere here. So this is the area view. If you look at a cross section, what you see is conduit, a large chamber, and there are all, of course, other underground rivers, channels. So you have waters flowing here, and also these are porous medias. Although they are rocks, they are not that kind of rocks. They are different kind of rocks. These kind of rocks, limestones, they are still porous. Okay, so waters also flow there, and why we care about that? Besides, people film the things, and the spring is nice, but it's a problem. We just avoid that. The reason that we care about these things, among other things, is we draw a large percentage of our drinkable water from these resources. So here is a schematic plot. So you have the so-called Karst aquifers. So essentially a large cave underground, and then water is stored there. But this is not an isolated system, so they are sort of related to what's happening above it, and eventually related to what's happening at the surface. So whatever we dump eventually would affect the water quality down there. So, so that tells us we have to consider the system as a whole. I mean, flows or water flows in these so-called Karst aquifer, and water flows surrounding it. So in particular, not in North Carolina, as you can see, there are a lot of Karst aquifers around the country. In Florida, it's essentially everything. So Florida, we depend on Karst aquifer 90%. The whole country is 40%. So it's a serious problem, and you see why problems would arise. For instance, you have a sinkhole, you have an underground river, you have a spring, and then when it rains, you have high flow here. Then the pressure in this underground river or conduit will be higher than the pressure in the surrounding rocks. So then water would flow to the surrounding area, and whatever the contaminants that's on the ground, let's say your fertilizer or whatever, comes with the runoff, goes into the conduit. You thought it would just go to the spring, but it would some of it would go into the porous media around it because of this sequestration process. Then when the rain stops, the water table goes down, and then the pressure gets lower in the conduit, so the pressure reverses. So the pressure in the ambient matrix is higher than the pressure in the conduit. So flows would flow from the matrix to the conduit. That's why even though it's not raining, you will still see water is coming out of the spring. Okay, so but then with these flows, whatever the contaminants that's stored in the matrix will come out as well, and that's what we observe in our neighborhood, the Ocala Spring. What's observed is excessive nutrients in terms of nitrogen, and the weeds will overgrow in the spring.
What do you call the matrix?
It's the porous media, but in groundwater they call it matrix. Okay, so this kind of geometry is not just limited to groundwater study. So here is another example, a proton exchange membrane fuel cell. So in this case, you have in fact two sets of sort of caustic geometry. You have a channel here that have hydrogen flows. Then you have a porous media layer, and then over here you have another channel that you're pumping oxygen, and you have another porous media here. In the middle, you have a platinum layer that induces the flow of electrons. You see, so for this side of the cell, the oxygens flow here, that's what fluid flow. But in this prosymedium, the oxygen and the hydrogen and the electrons would combine and react to form water. So there are multi-phase fluid flows in this multimedia, in this prosymedium. And so although the setting is hard, the whole dynamics is complicated, but the geometry, as you can see, prosmedia, conduit, flows in prosmedia and a conduit, they interact with each other. Okay, so we have these kind of geometries pop up quite often. So what's the main issues? The main issues are, of course, you want to know how the flows flow in the conduit or the underground river, how the water flows in the matrix or the prosmedia, and more importantly, how do they interact with each other. If you ignore the interaction, essentially we all know what's happening. So here is a setup of the geometry that's sort of easy to understand. So you have a conduit, and you also have a cave here, or so-called fog. And surrounding it, it's all porous media. And you have the interface between the conduit and the matrix, called gamma I for interface. So this is also gamma I. You have the unit orthonormal to your conduit. And the gamma M is the boundary of your matrix, except this interface part. And the gamma C is the boundary of the conduit, except the interface part. Okay. So if we focus on the conduit or the caves, we know what's the dynamics of the governing equation. It's the Navier-Stokes equation, because the fluid flows underground. Usually it's not that high, so incompressible. Navier-Stokes equation. And if the fluid flow is velocity is really low, then you can even forget about these nonlinear terms or the time derivative to deduce the so-called Stokes equation. So for the students who have not seen this thing before, the notations are: the rho zero is the density of the fluid, in this case it's water, and the V is the velocity of the fluids. So C, just the subscript C represents conduit, and the T is the stress tensor. It's related to the rate of strain tensor D, and the pressure PC, and the viscosity eta. So this is a baby fluid dynamics that you learned for Newtonian fluids. They are related in this way. So the stress tensor is twice the viscosity eta times the rate of strain tensor minus the pressure times the identity. Okay, so this is the Navier-Stokes equation. We treat it as incompressible, and if you forget everything else, the most natural boundary condition is the so-called no-slip boundary condition. So fluid sticks to the boundary, so the velocity is zero. If you agree this is a good model for flows in conduit, then you can easily check the kinetic energy is dissipated, and the rate of dissipation is exactly the viscosity times the rate of strain tensor squared integrated over the whole domain. Okay, I emphasize this part because in the theory below, I will use this to derive the equations. Now, this innocent equation of system of equations I presented here, as most of you know, has at least $1 million behind that. So we will be focusing on the simple part without the nonlinear term. Okay. And for physical reasons, it's justified because my velocity is relatively small. Okay. So, and these two are the two guys who are responsible for these two equations. A Frenchman and an Englishman. The Frenchman is a very good mathematician, but I heard that he's not a particularly good engineer. The bridges that he designed didn't last very long. Now, how about flows in the porous media or in matrix? Then we have a set of equation called Darcy's equation. This set of Darcy's equation can be derived from the Navier-Stokes or Stokes equation using various ways. So essentially, it says the velocity is proportional to the gradient of the pressure in the porous media, and in the negative direction, of course, with a constant or tensor k. The k is the so-called hydraulic conductivity. If it is of a homogeneous isotropic media, k is a constant. If it is inhomogeneous, then it's a function. If it is anisotropic, it's a tensor.
Okay. One question.
Yeah.
Why do you often cross some terms?
Okay, so I included this term for the purpose to see, this is heuristically a low order term, but if I include this, then you can see the energy is dissipated with the rate of this. Okay, so if I cross out this term, then it's harder for me to say what's the energy dissipation rate. Okay.
Yeah, but when you cross this term out, there's no time dependence. You're not doing even.
Yes, I won't be having time dependence, but in my theory below, I will be using Helmholtz minimal dissipation principle to derive the coupling of this Darcy's equation and the Stokes equation. So the interface boundary conditions, where do they come from? So in order to use Helmholtz principle, as you will see in a few slides, it says fluids are smart. They would like to minimize the dissipation of energy when they have their configuration, if the Reynolds number is small. But in order to apply that, I have to know what is the energy dissipation rate. I can just say this is the energy dissipation rate, but I think if I include this lower order term, then it's easier to see this. This is the energy dissipation rate. Okay. And so this is lower order than each one of these.
So are you looking for a stationary solution?
No, eventually it's not stationary. But to start with, we can look at the stationary. In fact, the two-phase models has to be time dependent.
So what is lambda?
Say it again.
Lambda?
Chi. This is the porosity. Okay, so sorry, so for notation here, rho 0 is still the density. Vm is the velocity or the Darcy velocity in the matrix. Pm is the pressure in the matrix. Eta is still the viscosity. Chi is the porosity. So porosity is how much, what's the percentage of the void space in your matrix. Okay. If it's 1, essentially you have no structure, right? So you have free flow. If it's 0, then you have steel. No empty space between the structures. So that's Chi. That's called porosity. And
very porous media.
Porous media, usually that's a subtle issue. If even if it's very porous in the sense of the pore space, the portion of void is large, it doesn't mean fluid is easy to flow through that. You could build, say you have one sheet of steel that blocks the whole flow, right? The volume is 0, but it's not flowing through that. So, but the counterexample that I give you is a sort of a non-generic example. In generic case, the higher the porosity, the easier for the flow to flow through the structure. How easy it flows through the structure is characterized by this permeability. So this is the capital pi. And the capital pi is related to the chi under generic circumstances. That's what I quoted here, common Cassini formula. Then if you know the permeability and the viscosity, you can determine this coefficient here, so-called hydraulic conductivity. If you retain this low order term, as you can see, the energy dissipates with a rate of this. Okay, so this is I will utilize this energy dissipation rate in the matrix later. So these are all well-known stuff. And this is Henry Darcy. He's an excellent engineer. So how do we couple these two systems? Both systems are very, very well known. We know they work very well. So one of the coupling condition is easy. You have to have conservation of mass. So that means whatever leaves one region has to go into the other region. So the normal velocity has to be continuous. Okay, so that's easy, right? So the other interface.
Excuse me. Why isn't there a factor of 5?
I'm sorry?
Suppose you've got water going from the conduit into the matrix.
Yeah.
You need a factor of 5 in that.
That's true. So that's why this is a sort of caveat that I listed here. So this velocity, Darcy velocity, is not it's not the real velocity. The real velocity is the seepage velocity, which is this. Right? Okay. So you're absolutely right. But then if you consider seepage velocity, the area has to be multiplied by chi as well. And that mathematically, in fact, it's not proved. It's a sphere packing problem. Can you show really, statistically this is true. If you have a porosity of chi, then the area you slide. The void area should be proportional to chi, but it cannot be proved. It's not known. Okay, so one interface boundary condition is apparently not enough. You count the fingers, right? You have how many unknowns? You have in the porous media, you have the Darcy equation. So essentially, the pressure is the unknown, right? And then in the conduit, you have the velocity that's unknown. So even in two-dimension, velocity is a vector too, right? The pressure in the conduit it can be viewed as a function of the velocity. So you don't count that, but at least you have 3 unknowns. So in order to have a well-posed problem, you need 3 boundary conditions. And smart people have thought about these questions before, so they know you need to have core boundary conditions, interface boundary conditions. So one of the boundary conditions that proposed by these 2 guys, Beavers, Gordon Beavers and Daniel Joseph, long time ago, is this. So what does it say? It says essentially, on the interface, because one side is porous media, other side is free flow, so the fluid could glide along the interface. sort of like you have porous medias. Think of it, you have waters over there, so lubricates the boundary, so you can glide a little bit. So that's why this velocity of your fluid velocity in the conduit projected onto the tangential direction at the boundary may not be zero. Right? Okay, so but how it when it glides, of course there should be a force that resists this this movement. So this is friction, and you say so the way that you write it is the tangential component of the normal component of the stress is proportional to the jump in the tangential derivatives. Okay. And then you have the parameters of the numerator you have viscosity there, and the denominator is related to the trace of the permeability tensor. If it's just scalar, you just add it. Beaver Joseph didn't write it this way. What they wrote is more like this. So let's say hypothetically the normal velocity is zero. So what they said is negative of the viscosity times the normal derivative of your tangential velocity is proportional to the jump of the tangential velocity between the conduit and the matrix. So this is the usual friction norm, right? This condition has been puzzled many of us for a long time. Essentially for 40 years, nobody was able to do any analysis on that. But also in terms of physics, it's also hard to do that, to work with that. So again, other smart people, this is another guy, Softman. He said, looking at this, either this condition or this condition, the velocity in the porous media is usually much smaller than the velocity in the conduit. So why don't we just omit the red part? So if you omit that part, what you end up with is this so-called Beavers-Joseph Softman-Jones interface boundary condition. Jones, his contribution was, the first three guys all wrote it without this term, like this, flat boundary. Jones was able to write it in terms of the stress tensor, so it was much better. Interpretation is better too.
So I mean, an interpretation of this is just that the flow in the conduit tangential induces a shear stress.
Yes.
In the matrix.
Yeah. So
Darcy's law is on the right hand side. So the right hand side induces a stress.
Yes. That's the So these are the people. I don't have a picture of Jones, but these are the people who are responsible for that formulation. So Daniel Joseph, some of you probably know, he's one of the guys who was a member of the National Academy of Sciences and a member of the National Academy of Engineering. So he, one amazing guy. So that's his colleague, Gordon Beavers, and this is Philip Softman. He's one of the well-known guy in fluid dynamics, especially in terms of vortex dynamics and fluid flow in porous media. And these two guys not only proposed that Beaver-Joseph interface boundary condition, they conducted laboratory experiments, verified this interface boundary condition. They calibrated these coefficients, okay, so for different readings. So it looks pretty good. But still, it's not enough. Why it's not enough? In 2D, this just gives you one more interface boundary condition. You still need another one. So what's the third one? Now it's a little bit more controversial. Different people propose different theories. So one group of people proposed that the normal component of normal stress should be balanced in the sense of, in the fluid, this is the normal kind of normal stress equals to the pressure in the porous media. So that's one theory. And then the other theory says, but you know, the pressure should be continuous. There shouldn't be any discontinuity in the pressure. But which one is the right one? Right? So then there is a group of mathematicians try to solve the problem from homogenization point of view. So Jaeger and Mechanic, they looked at the problem from the homogenization point of view. They looked at 2D only, assumed that here everything is periodic, and here you have to impose a uniform velocity. Here you impose a uniform velocity. Then they can show that you can perform the homogenization procedure. And it turns out the boundary condition that you recover is this one. Okay, so it's not this one. Okay. And we used
Meaning by homogenizations is in what sense? So multi-scales.
Yeah, so here you have free flow, okay, conduit, and you have your Stokes equation with the boundary condition specified here and here. And here you also start with Stokes equation, but you know, in this periodic structure, right? So when you zoom out in this part, so essentially you say shrink these sand particles, and keep the ratios unchanged. Then you can derive an effective equation, an effective boundary condition. The effective equation, of course, it's the Darcy equation here.
Yes.
No doubt about it. Here you're not changing anything, so Stokes is still Stokes. Then the interface boundary condition is what I wrote here. Continuity of the normal velocity. Beaver-Joseph Stuffman-Jones. That's the slip at the boundary induces a shear stress, and then the balance of normal stress. So that's in the limit, and but that's under the assumption that it has to be 2D. These guys do not know how to do 3D. 3D is much harder, and you have to have periodic structure, and you have to have impose polyflow. So if we use this model with the three interface boundary conditions, in fact, we can perform numerical simulations. So here I cited a few works. So Porteroni and his former students, this guy, I don't know how to say his name, they started this business first. So they used the brutal force method solving those problems. Then we followed up with so-called domain decomposition method. But that domain decomposition method is probably different from people here understand that. What we meant is, for our problem, we have two physical domains. One is Darcy, one is Stokes. So the most natural thing to do is you have a solver that only involves Stokes solver and Darcy solver. And we were able to design that kind of numerical scheme. So in that sense, the domains are decomposed. And first order, second order accuracy, unconditional stability, we have all of them. And here is a numerical result that we have. So this is the lab result. The lab result is poor. So I was talking to Mark. It took our collaborator a long time to come up with this. So it's a sandbox on top. It's a channel in the bottom. And the red things are the dyes. So we let the water flow here, and then the dyes will go into the sandbox. So you see the double hump of shape, and this is the numerical simulation. So according to eyeball measure, it's pretty good. Okay, eyeball measure. Okay, so looks good. Here I would like to ask the question: is there another way to derive these equations, especially the interface conditions? I know that Beavers and Joseph proposed heuristically, ad hocly, verified it empirically using their experimental data, and then derived using homogenization theory, but under very stringent conditions, which is usually not applicable in application. So the idea that we have is applying Helmholtz minimal dissipation principle. So that's what Helmholtz said is, if you look at the steady flow, and if the speed of the flow is small, then the configuration of the fluid flow must be something that minimizes the dissipation of the energy. Okay, so that's what he said. Essentially, heuristic says the fluid is smart. It doesn't want to lose the energy. So to change its configuration to minimize the energy loss. And that heuristic is correct. And you can verify this is the correct idea, at least in terms of consistency with the Stokes equation. So in the Stokes equation case, we already know this is the dissipation rate of the energy. So eta is the viscosity, dV is the rate of strain tensor. So this is how fast the energy is dissipated, right? So you want to minimize this, but under the constraint that the velocity field must be incompressible. If you want to avoid incompressibility, then you just add the Lagrangian multiplier. So then you do your math, you recover the Stokes equation with the Lagrangian multiplier identified as the pressure. So that's, of course, we teach our first year graduate students. But the point here is Helmholtz variational principle works. At least it's consistent with the Stokes model. So what do we do for our coupled system of Darcy flow in matrix and a Stokes flow in the conduit? So we need to know what is the energy dissipation rate. So that's why I emphasize those 2 points. So this is the energy dissipation rate in the conduit or in the underground river. It's the same as in the Stokes equation. And this part is the energy dissipation rate in the matrix or in the porous medium. That I also sort of emphasized, why I kept the red term then put a cross, because this tells me this is the energy dissipation rate in the porous medium. On top of that, because the fluid is gliding along the interface between the matrix and the conduit, that slip induces some energy dissipation. Okay, so this is the energy dissipation related to the friction along the interface. If it's no slip, then Vc tau, this is the tangential component of the velocity, will be 0. So this wouldn't be there. But if it's not 0, then this is energy dissipation. And it is subjected to the incompressibility condition, and also the normal velocity must be continuous because of mass conservation. Then you do your math. Sure enough, you recover the Stokes equation in the conduit, and then the Darcy equation in the porous medium. And the Lagrange multipliers are exactly the pressures. Okay. And moreover, the interface boundary conditions comes out naturally. So this is the Beaver Joseph interface boundary condition. Just to write it in a slightly different form. The beta is this. Okay, and this is the balance of the normal component of the normal stress. Okay, so these are the two interface boundary conditions that we derived out of the variational formulation for the minimum dissipation. And this is what we impose. It's a physically correct conservation of mass. From this exercise of one-phase flow, what do we learn? We say Helmholtz's minimum dissipation principle is a very powerful tool, at least the way we can recover these interface boundary conditions using this principle. And we have also derived efficient numerical methods to simulate these problems. The more interesting problem is a two-phase problem, because what I have shown you, the pictures that I showed, I have a water table, for instance. Water table, then it's the phase, two-phase between water and air. So what do we do with two-phase? Well, two-phase problem is a much harder problem. So we just started this process. So there are at least two ways of approaching two-phase problems, two-phase immiscible problems. So a way of doing that is a sharp interface approach. You say, the black and the white, they never mix, not even a little bit. So we have local experts here work on these things. I think you heard of these things quite a bit. So what I'm going to do here is an alternative approach, so-called phase field approach. So instead of saying you can only have black and white, I say it is also possible to have gray. So in other words, most of the time, here it's just a white or black, so fluid 1, fluid 2. But along the thin, very thin region, the two fluids could mix just a little bit. It's impossible to have completely immiscible one. This theory, of course, is not new. Smart people have thought about this a long time ago, back when really Laplace, right? And more recently, this phase field approach can be formulated using Ginsburg, the Landau type of free energy. So you say, you impose a free energy that looks like this, where epsilon is a small parameter. So this part of free energy is a phobic part, so wants to separate the two phases. If you want to minimize this part of the energy, phi has to be 1 or -1. Let's say 1 corresponds to here, -1 corresponds to here. But this part also tells you, if you want to minimize this, phi better be a constant. Right? So this enhances mixing. So it's a competition between these two, but we put a small parameter here, so you see most of the time this thing is more important. So that's why we will see the phenomena mostly like this. And if you look at this energy, look at the gradient flow of, in the L2 norm, then you have the Alan-Kahn dynamics. If you look at the gradient flow in the H-1 norm, then you have the Kahn-Hilliard dynamics of, related to phase separation, as many of us know. Okay. So if you take this phase field approach, there are also very well accepted models, two-phase flow models in the conduit. So that's the so-called Kahn-Hilliard Navier-Stokes equation, or sometimes Navier-Stokes Kahn-Hilliard, depending on whom you like more. So this is the set of equations. So the UC is the velocity in the conduit. The T is again the stress tensor. and the phi is the so-called phase field parameter, but that's specified here. Phi essentially is 1 in one phase, -1 in the other phase. Okay. So rho is the density. Without this term, what you have is exactly the Navier-Stokes equation. Okay, so this term is the elastic forcing term or the capillary forcing term. But instead of having it located on the interface, sharp interface only, now it's a distributed force. Okay. Okay, so and the mu c is the so-called chemical potential. It is related to the Ginsburg-Landau free energy. It's essentially the variational derivative of that. Okay, and you have a parameter there, gamma, because the variational derivative does not have the dimension of chemical potential, so you have to have a function parameter over there. So that's the Navier-Stokes with elastic forcing. Then the phase field has to evolve as well. So the phase field apparently will be vectored by the velocity field, right? And then on top of that, it is diffusive. So the diffusion is using the Karst-Hilliard dynamics. So the m is the mobility. If you write this down, ignore this term. It's exactly the Karst-Hilliard dynamics. So this is well known of a set of a system. Many people derived this set of system using different methods. I have cited a few people here, and if you're interested in this review paper by Anderson, McFadden, Wheeler, it's very readable. And Lowengrad and Chuskinowski has a very nice mathematical derivation from the mixing of two fluids. I have to say a few more words. Phi is the order parameter, volume fraction essentially. Then you can define the rho is really the mixture of the density of the mixture of the fluids. So what you heuristically is here is the formula, the density of the mixture. And you can define the viscosity. You can believe the viscosity is also a function of the viscosity of two fluids and the volume fraction. Okay. And the small parameter of epsilon is essentially the interfacial width. So related to here, so you see there is a blurry region, the width of it is the epsilon. And you can look at the balance of these two. See a transition layer is an epsilon. Okay, so that's a phase field model for two-phase flows in the conduit. What happened in the matrix? In the matrix, there is a parallel theory, so it's the so-called Karst-Hilliard-Darcy system. So this is the Karst-Hilliard-Darcy system. Instead of having the Navier-Stokes equation, you write down the Darcy equation. So the Darcy equation is forced by a elastic forcing term as well. And then this is the Karst-Hilliard equation if you ignore this advection term. So you have this, and but you can find the derivations of these equations in these references, for example. So again, the question is about how do you couple these two, right? So the way that we couple these two would be using a generalization of Helmholtz principle. So a generalization of Helmholtz principle that's suitable for this purpose is Ansager's extremum principle. So what he says is for fluids near equilibrium, the configuration is to minimize the sum of the total energy dissipation function and the rate of the change of the free energy. So energy dissipation rate plus the time derivative of the free energy. Essentially, that's what it says. Its original formulation, in fact, is not about free energy. It's about the entropy. But you know, for the system, for mechanical system that we work with, it's better for us to use free energy. Some of you, I mean, probably most of you know of Ansager's reciprocal relation. It's derived using his extremal principle. So that's his Nobel Prize winning work. It's derived using this simple principle. Okay. So again, you can interpret his principle as fluid is smart. It wants to do little work. So minimize the energy dissipation rate. Change as little as possible in terms of free energy. Okay. So we can apply his principle to the two-phase flow problem that we have. Just we need to formulate it in the right manner. Okay, so I'll jump a little bit. Essentially, you know, you can introduce what are the rates. You know, the rate functions of one of them is of course the velocity. The other one is the chemical flux or chemical diffusive currents. There are natural boundary conditions. Then there are also natural interface boundary conditions. For instance, you know, conservation of mass across the interface. Even in this two-phase setting, you can deduce that the normal velocity has to be continuous. Just a simple algebraic manipulation. Okay, so and then the order parameter or the phase field of a function phi also needs to be continuous across the interface. The dissipation functions, what we have is we impose is the following. So in the prose media, this part is the dissipation of the energy, exactly the same as in the one-phase, single-phase model. It's just related in a slightly different way. Okay, the hydraulic conductivity is permeability over the viscosity. Then, because of the two-phase problem, you have the chemical diffusion. You have an additional dissipation. So this is the additional dissipation that's due to the chemical diffusion. Okay. And likewise, the dissipation function in the conduit also changes. So this part corresponds to the one single phase part. This also corresponds to one single phase part. That's the dissipation along the interface. This part is the dissipation due to chemical diffusion. Okay. So you add this, then you also have the free energy. So the free energy is the Ginsburg-Landau free energy. So the time derivative of the rate of change of the free energy you can compute for the conduit, for the matrix. You apply Ansager's principle. You minimize the energy dissipation within the matrix, energy dissipation within the conduit, rate of change of free energy in the matrix, rate of change of free energy in the conduit. Minimize this. You can ask a graduate student to calculate this. It's a good exercise. And we derive this set of equation. So it's exactly this. This is the Darcy equation with this elastic forcing term, and this is the Carhelian equation with advection by the velocity for the cross median. We will cover the Stokes equation with the additional elastic forcing term, and this is the Carhelian rate conduit. And the interface boundary conditions are the following. So it turns out to be no surprise in this simple formulation. This is imposed from a purely kinetic consideration, conservation of mass. You have the continuity of normal velocity, continuity of the phase field. Then the normal velocity, normal component, normal derivative of the phase field is also continuous, and the normal component of the normal derivative of the chemical potential is also continuous. And then these are the point is this is the Beaver-Joseph Sussman-Jones interface boundary condition. This is the balance of normal component of the normal stress. So so we have that formulation, and the nice thing about this formulation is, one of the nice things, a consequence, is an energy law. So we can show that the free energy, the total free energy, is a decreasing function in time. And what's good about that, the good thing about that is now we can design numerical schemes that respects that energy law. So that tells me if I do numerical simulation with those numerical schemes, I wouldn't have blow-up problems. And that's a very desirable feature, because we know for these interface boundary conditions, we have experts here, it's really, really stiff. If you do explicit methods, it's so stiff, many times it blows up. Okay. So we have the numerical scheme design, and we can also generalize the simple setting to more general case, taking into account more physics, but the numerical simulation is still underway. So to summarize, we see that Ansage's extremal principle can be used to handle this kind of two-phase flows in this Karst geometry. And the new model that's derived has at least one very desirable feature, energy law. And numerical schemes can be designed that respects these energy laws, but numerics is still underway. So there are a lot of questions to be answered. For instance, whether this system is well posted. You have an energy law doesn't mean it is well posted. Like Navier-Stokes equation has an energy law, but $1 million is there if you can show it's well posted. Right? What's the relationship between this phase field model and the sharp interface models that people here and many other places work on? The numerical method that respects the energy law that we designed is not very efficient. Is there a way to design more efficient ones, like what we did with the single phase one? Single phase one, we have decoupled the numerical schemes. Stokes solver, Darcy solver, at each time step, you solve each one of them separately, so you can parallel them, then after you do your calculation, then do commutation at the end. Can we do that? More importantly, how good this model is beyond the mathematical well-postedness. You have 3 parameters there, so can you calibrate these parameters in a good way so that this is experimental data? Okay. And you have uncertainties in both in terms of hydraulic conductivity or the porosity and the geometry of the conduits. So all these things, future problem. Thank you. Yes.
So the uncertainty in geometry, that one's a really hard one. I mean, that plagues hydrology at all levels. How does one even start to approach that?
The naive idea that we have is we say there are only certain shapes that we will consider. So just like parameterizing a curve. It's infinite dimensional, but I say, you know, a few modes. But it's far from the reality. So we are still struggling how to come up with something reasonable.
The double Wang potential that
Yeah.
you use was sort of the default
Yeah.
in this phase field approach.
Yeah.
But,
Yeah.
I mean, it's not based on anything physical. You just
That's true. There's an alternative way of using the logarithmic potential. So
is there a justification in the context of Darcy?
this is it's purely heuristic. Formally, I can take forget about the coupling, the two-phase Darcy. I can formally take the sharp interface limit. Do my formal asymptotics, I recover the Muscat problem. So two-phase sharp interface.
But I mean, that doesn't depend on the choice of double Wang potential. Because
Well,
you really just get the two.
Yeah, you only need that's true.
I mean,
That's
as
true.
long as they're located, right?
Yeah, you have to have two well with equal depth. Just the Ginsburg-Landau potential seems to be a convenient one to work with. There are many others that works. The logarithmic one is more appealing because you can sort of derive it from a statistical physics. But that one, you know, in the small regime, you can do Taylor expansion to cover the Ginsburg-Landau. But the application is not in that regime, so it's not self-consistent. Yeah. Okay.
Do you have an application in mind for the two-phase problem? What two phases are we talking about?
Oh, so it's air and water. The density difference is huge. So then the phase field model, you can still have phase field model, but it cannot be treated as incompressible. At the interface, it's cannot. You have to use compressible model. The compressible model, we are still working on it on how to derive numerical scheme that respects the energy law. So this is relating to beyond the Boston-Scott approximation.
Yeah, I think this is beyond the time now. So let's thank the speaker.